Hi, my name is Winston Wu, and I am a high school junior at Northfield Mount Hermon. My research project is focused on the machine learning classification of stars, galaxies, and quasars. There are three aspects of significance to this research project. The first of them is astronomical classification, and its significance lies in that for astronomers to study the different types of celestial objects in the universe, large amounts of data samples are needed to perform the necessary analysis. And because of this, classification becomes a very key step in turning the collected data into actual usable data samples that are useful for analysis and study. The second aspect is the specific use of machine learning classification, and this is because modern telescopes are recording data at increasingly high speeds, and this makes it more and more impractical and inefficient for the classification of astronomical data to be done by hand, as algorithms can do this task with very high speed and much higher accuracy. They are a very ideal candidate for this task. And the last aspect is the use of photometric data. As opposed to spectroscopic data, which are easier to classify but much harder to collect and record, photometric data are the exact opposite. They are easy to record and collect, but much harder to classify. However, this actually creates another great reason to use machine learning classifiers, as algorithms can detect the less distinct differences between the different objects in photometric data. And with its large data sample sizes, because it is easier to collect, photometric data actually becomes a very ideal data type to use to train machine learning classifiers. The objective of this study is to create a predictive model to classify stars, galaxies, and quasars. A subsequent aim is to compare and contrast the performance of different machine learning algorithms, specifically logistic regression and decision tree. My hypothesis is that it is possible to successfully train a high-performing machine learning model to classify stars, galaxies, and quasars using specifically the astronomical data from the Sloan Digital Sky Survey, or else abbreviated as SDSS. The methodology that I used has four parts. In the first part, the data. So the data set is the data release 14 of SDSS, and after variable selection, the remaining variables are 6 feature variables and 1 class, or the dependent variable. Of the 6 feature variables, they are each the UGRIZ and redshift. The first 5, UGRIZ, are so they each measure the intensity of light of a specific wavelength, which is data about the color of light that the celestial object is emitting. And the last one, redshift, it measures how fast the celestial object is moving away and how far it is relative to Earth. The second part is the exploratory data analysis, and in it I calculated the variable correlations, the class counts, and the distribution of the data set. Third is the pre-processing phase, and in this I standardized the data set using the min-max scalar, as the dataset's distribution is not normal distribution, as the graphs will show later. And lastly, in the machine learning phase, I first split the dataset into a training and testing sample. I then train the multinomial logistic regression model and the decision tree model using the training sample, and then using the testing samples, I calculated the performance metrics of these models, and the results were the classification reports, the cross-validation scores, and the confusion matrices. In the first part of the results are the graphs calculated for the dataset, and the first of them is the heat map of the variable correlations. In this heat map, the one issue that is possibly raised is the concern for the few high correlations between the variables. As we can see here, the high correlations of 0.96 and 0.97 exists mostly within the variables UGRIZ. And while it is generally agreed that independent variables should not have high correlations, or else they won't be independent, and the performance of the model could be hurt by this. However, each high correlation needs to be examined case by case, and in this case, while we could remove one or two variable in UGIRZ to remove the high correlation. However, the UGRZ are actually the 5 key color filters of the CCD camera system of SDSS. So this means that the removal of any of the 5 variables could result in significant information loss that could hurt the performance of the models much more than high correlation ever could. The second graph is the distribution plot of the feature variables, and they are separated into each feature variable, and they're further split by their classifications, as shown by the 3 different colors. And as you can see here, none of them follow a normal distribution, which was the reason why we used the min-max scalar. And lastly, this is the count plot of the 3 classifications. And while concern may be raised that the quasar classification is relatively less in count than star and galaxy, possibly making the data set unbalanced. However, the ratio of count here is actually 4 to 5 to 1, which is actually not considered to be an unbalanced data set. Furthermore, several of the performance metrics that are used to gauge the models, they are specifically well adapted to unbalanced data sets. Next is the results for the performance metrics of the multinomial logistic regression model. And the first is the classification report. And in this, several performance metrics are shown, such as the precision, the recall, the F1 score, and the accuracy, as well as their different averages. And as you can see, all of them have a score at least above 0.84, and with a max of 1. This means that the logistic regression model has a fairly high performance in the task of classification. However, while generating this report, a convergence warning appeared. And this warning down below here could mean that the hyperparameter needs to be adjusted, or that the maxed iterations needs to be made higher. But despite that, fixing those possible issues could resolve this warning. The fact that this warning appeared it could mean that the logistic regression model we're using has some intrinsic unfitness to the data set we are using. Next is the confusion matrix heat map of this model. And this shows the number of objects that are correctly classified and the number of them that are incorrectly classified, as well as the wrong classification they were predicted to be. One issue possibly raised by this graph is that we can see a concentration of wrong predictions in one classification. As you can see here, there is about 130 objects that are actually galaxies, but were predicted to be stars. And the same case here, except they are actually stars, but wrongly predicted to be galaxies. And this concentration of wrong classifications in one type could mean some intrinsic problems also. Lastly is the cross-validation accuracy score. And this measures or estimates the model's real-world performance, and it also measures whether the model was overfitted to our specific training sample. But as you can see here, the accuracy score has a very high 0.8664, which is very close to the accuracy score we got in the report of 0.87. So this means that the model's performance, as shown in the table, will transfer very nicely into real-world performance with very little loss in performance. Moving on to the results of the decision tree model. First, with the classification report, we can immediately see that all of the metrics in the report are significantly higher than those of the logistic regression model, as some of the metrics have reached the max of 1, which means perfect classification, and some even reach 0.99, which is very close to 1. And this by itself alone signifies that the decision tree model has some superior performance than the logistic regression model. Next, in the confusion matrix heat map, we can see that the logistic regression model's slight issue of the concentration of wrong classifications does not exist in the decision tree model's performance, which is also an improvement over the logistic regression model. And lastly, in the cross-validation accuracy score, we can see that this is also significantly higher than that of the logistic regressions, and it also maintains a very close proximity to the accuracy score we got in the table, which signifies that the decision tree model still has very, very high real-world performance. And with all of that, it can be concluded that the decision tree model is significantly superior to the logistic regression model, and that the decision tree model itself is an extremely well-fit and accurate classifier for stars, galaxies, and quasars. Thus, my hypothesis of being able to create a high-performing machine learning model for the classifications of celestial objects using SDSS data is proven to be correct. Lastly, the decision tree model created from this study, because of its high accuracy and performance, I am very confident that it can be a very competent and reliable classification tool in many astronomical purposes, and the most direct one being to increase the sample size of stars, galaxies, and quasars, as it has very high speed as well as very impressive accuracy, making it a very fit and competent tool to accomplish this task. Thank you, and I hope you enjoyed my presentation of my research project. Thank you again.